Hey everybody, this is lesson 8 on kinetic theory of gases. Uh, continue on the discussion with thermodynamics. If you remember, one of the things I said that we're going to be doing in this topic is we're going to have to look at what's going on at the microscopic level and how that relates to what's going on at the macroscopic level. So that's what we're going to be talking about today is pretty much like how are things like pressure, temperature, how are they related to what's going on in the nitty bitty microscopic level. And that's what we're talking about when we say kinetic theory of gases. So, first, the main idea that we have to discuss is the fact that remember that a gas is composed of a bunch of molecules, a bunch of atoms that are moving around at a constant but random motion. They are constantly colliding with each other and they're colliding with the container. So, for example, you can see it here that if you look at one of these particles, it's constantly bumping into stuff. Now, because of the fact there are so many particles moving in so many different ways, colliding in so many different times, what we end up having to do is we have to approach this through what's called a statistical approach. Basically, talk about what's going on an average and look at the big picture, and that's what's going to tell us what's going on at the big level, the macroscopic level. All right, so now there are a few assumptions that we want to make right off the bat. Like, first, we're dealing with a large number of molecules, so at least a mole, maybe even more, of particles. And they all have a certain mass, and we're going to say that they are moving with a random motion of a variety of speeds. So they're not all moving with the same speed. Now, the next assumption that we're going to make is that the distance between molecules is much larger than the size of the molecules themselves. This is basically going to mean that there's really not going to be a whole lot of interaction between them. They will collide every now and then, but not significantly. Another thing is that the molecules are, we're going to assume that the molecules behave as classical particles and they only really interact when they collide. So this kind of goes back to why we're considering the distance so large compared to the size, is so that we don't have to really consider these intermolecular forces between them. So pretty much we're going to assume that there are particles that when they interact, it's only through a collision and then they bounce back off. And then going along with that, we're going to also assume that the collisions are perfectly elastic and occur over short periods of time. So these are all our assumptions, which kind of works with the whole ideal gas part. Now, if we look at this and we think about it, when these particles are moving around, they're going to bump up against these the walls, the surfaces of our container. Now, this bumping is going to result in a force that acts on the container. These constant bombardments of the particles banging into the walls are exerting a force on each and every surface, which is basically going to result in a pressure being acted on the container. So right off the bat, just from this concept, we can already see why increasing the temperature will end up increasing the pressure on the system. That as we increase the temperature, we're causing the molecules to move around more chaotically. They're moving around with a greater speed. Because they're moving around with a greater speed, when they bump up against the wall, they're going to exert a greater force on that wall. And a greater force is going to result in a greater pressure because pressure and force are directly related. So that's where that whole increase in the temperature increases the pressure comes from. And we could also see that if we increase the volume, that's going to end up decreasing the pressure on it because now the molecules will have to travel a lot further to the surface, resulting in not as many collisions occurring on the walls. So again, a lot of the stuff that we've talked about, the stuff that's going on at the macroscopic level, the pressure, the temperature, PV equals nRT. All this can kind of be seen to make sense when we start thinking of gases in this kinetic theory type way of looking at what's going on at the microscopic level. Now, we want to actually come up with a quantitative result of, we set where we keep saying, or I keep saying that temperature is resulting in an average kinetic energy of the particles. Well, let's actually put that into work. So, first, what we're going to say is that when the particles collide with the wall, they're going to exert a force, and because it's elastic, we're going to use this equation that the force is equal to the change in momentum over the change in time. Well, because it's elastic, what that's going to tell us is that the momentum is going to remain constant, and that the kinetic energy of the particle is also constant during that process. So what we can say is that the change in momentum is going to be equal to the momentum it comes in at minus the momentum it goes out at. But since it's changing direction, that technically results in the momentum being twice its initial. So we can replace the delta P with 2m Vx. Now we're only looking at it right now in a linear motion, but we will end up taking into account all three directions. Now, the time until it hits the wall again, horizontally at least, is going to be equal to 2 times the length divided by this velocity that it's moving at. Again, it's not really changing its speed during this collision. So when we put these two things into the force equation, we end up getting at pretty much the force that one molecule is going to exert on the wall is equal to mv squared over L. And again, this is only what's going on in the horizontal direction. Now, because the three directions, X, Y, and Z, are considered independent of each other, motion in the vertical direction is not affecting motion in the horizontal and in the in and out direction. What we're going to say is that this equation is actually going to also be true for Vy and Vz. This is going to allow us to actually combine them all together. Now, right now we're only looking at the one molecule, and like I said, we weren't really considering its velocity changing during the collisions because of the whole elastic collisions. Now, we're going to start introducing more molecules. And we're going to sum over the average motion for them, because now that we're going to include more molecules, of course there's going to be a variety of speeds going on, and when they collide they're going to change their speed. But for the most part, because the particles are considered to be elastic collisions, the effect of the speed won't really change too much. All right, so if we do pull this out and we say it's true for all the molecules, what we end up getting is this. So we get the m over L, which is the same for everything, and then we get Vx1 squared plus Vx2 squared plus Vx blah 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 squared all the way to the nth molecule. What we can then say is that we can replace this phrase, which is Vx squared, the average of it, by taking all these squared terms, this sum of the squares, and dividing it by the total number n. One thing to note, this average bar is not just above the v, it's above the entire thing, meaning that we're taking the square of each term and then averaging it. So from this, what we can say is when we bring the n over to here, we can replace this sum of the squares with this, n times the average of the squares. And then, as I said before, this is going to be true in all three directions. So what we can say is that for the most part, the average in the x direction, the average in the y, the average in the z are all going to be same. Like I said, some may be faster, some may be slower, but the average should still be the same. So if I want to rewrite this as a way of relating to the total velocity, what I can say is that because each of these three terms are the same, I could just simplify it as 3 times the average in just the x direction. From here, I can then replace this term, this vx squared, average vx squared, with v squared, average v squared over 3. Then I can relate it to pressure. So pressure is force divided by area, which is getting me this. Because we have area times length, well, that's just volume. We can move the volume back over to here. And remember, we have the equation PV equal, what we can do here now is we have the PV term, and then we're just going to move some things around. So I'm going to move the N out, and because of the fact that I had mentioned that the temperature is going to be related to kinetic energy, I want to actually have a 1/2 mv squared. Like I can already see there's an mv squared over here. So I want to actually rewrite it as kinetic energy. But because this is a 1/3, I have to actually split this 1/3 into a 2/3 and a 1/2, just so that I can get that relationship that I want. So if you're trying to figure out where this 2/3 comes from and what's going on, all I'm doing is I'm taking this phrase, I'm moving the v out, and then I'm just splitting the fraction up into this part that's in front of the n and this part in front of the mv squared. And then as I said, because we have PV, we can actually set it equal to the ideal gas law, NKT. I'm using this one so that I can get rid of the number of molecules. So those cross out, and I end up getting this, 2/3, 1/2 mv squared equals KT. And as I said, I can replace this with average kinetic energy to get this equation. So this is the equation that we use to actually relate the average kinetic energy to the temperature. So I want to just quickly mention, I had said plenty of times that temperature is a reference to the average kinetic energy, but it's not kinetic energy, mainly because of this Boltzmann constant. This is going to make it so that it's not exactly energy. Like it's not they're directly related, but they're not technically the same thing. All right. So yeah. And also, I just want to remind you that temperature in this equation, because there's no delta, it has to be in Kelvin. So when you're using this equation, T has to be in Kelvin. All right. So work on this question. You can pause the video. We'll go over it in a second. All right, so they want to know the average translational kinetic energy. For now, you don't have to worry about it, but it's just that that equation is going to change depending on what type of kinetic energy we're going to refer to. For now, we're talking only about translational, so you don't have to change that equation at all. And in fact, you don't even have to worry about it. So what we have to do is first convert the 37 degrees into Kelvin, and then we just plug it into the equation, and we get that the average kinetic energy of a particle, or of the particles, is 6.42 times 10 to the negative 21 joules. Now for part B, they want us to basically figure out what the average is for an entire mole of gas. So what I'm going to do is I'm just going to take this and multiply it by the number of molecules, basically saying that if each molecule has this amount of energy, basically because it's average, timesing it by the number of molecules will get me a total kinetic energy of 3,860 joules. All right. Okay. So because of the fact that we're saying that the temperature is resulting in an average kinetic energy, we're actually defining a new quantity called root mean square speed. Now, if you've taken a circuitry course, you've probably heard the term root mean square before when dealing with AC circuits, so alternating current circuits. So if you recall, we had the equation of the average of V squared. So RMS is relating to this. So for example, I'll just pull this up. Typically when you have a kinetic energy, you do 1 half mv squared, and when you're trying to solve for v, you have to take the square root of um, 2 times k or whatever. Oh, I forgot the m. Yeah, so you have to take the square root of this. So essentially, that's what we do to find speed. Well, the thing is, the way our terms are, because of the fact that this is an average of v squared, when I take the square root, it doesn't actually get rid of this square. So that's why we have to define this as a very special and new term. Uh, Basically, the way you find the RMS speed is you take all the speeds that they give you take the square of it, you take the average, and then you take the square root. So RMS, you do it in reverse order: square everything, average everything, square root everything. All right. So I want you to figure out the RMS speed of the air molecules. So you can pause the video, work on this yourself, and we'll go over it in a second. So for here, all you're doing really is you're using the equation that was given to you. So we have to first figure out what the kilograms is. So we take this AMU terms, so the 32U and the 28U, and we're going to multiply by this 1.66 times 10 to the negative 27 to get the mass of the oxygen and the nitrogen molecules. And then to find the RMS speed, we're just going to plug it into square root 3 kT over m. Again, this has to be in Kelvin. And we get that the RMS speed for the oxygen is 480 and for nitrogen is 510. All right, so for this, it was a pretty standard plug and chug. Now, one thing I want to point out is that these are speeds. I keep calling these RMS speeds and not velocities. The reason why it's not velocity is because velocity is taking into account direction. And if we do take into account direction, then if the if the gas is not moving in a certain direction, then the average velocity is just going to be zero. The number of molecules moving up with a certain speed is going to equal to the number of molecules moving down with the same speed, and they're going to end up canceling out. So this whole RMS is really referring to the speeds. Now the way that actually works is actually one of the reasons why we're doing RMS speed rather than just taking the average of all the velocities. By doing this whole squaring it, averaging it, then square rooting it, we're actually taking the velocity and turning it into a speed that we can use. All right, so here what you're going to do is find the average and the RMS speed. So you can pause the video, work on this yourself. We'll go over it in a second. All right, so this goes back to what I was saying before about when you find RMS speed and you're given a bunch of numbers, you're going to pretty much do the square, the median, mean, and then the root. So first, we'll just take the average straight up. So that's easy. Add them, divide by the 8. So add them up, divide by 8, and we get an average of 3.6 meters per second. Easy peasy. Now for the RMS, well, first what we have to do is we have to square each of the terms. So we have to do 1 squared, 6 squared, 4 squared, 2 squared, 6 squared, 9 squared, 4 squared, 25 squared. And then divide it by 8, and then square root the whole thing. And we end up getting 4 meters per second. So when we do RMS, we actually do get a very similar number to the average speed, but it's not exactly the same. There is a slight difference. We're actually going to go back to that later on. Now, by definition, because of the fact that we keep saying that these molecules have an average speed, what that means is that some molecules are going to be moving faster and some are going to be moving slower. So there's actually a distribution curve for the relative speed or the speed of the molecules and how many molecules are moving at each speed. Like, for example, if this is referring to a certain gas of a certain temperature and a certain mass, what we end up having is Down here, there's not really a whole lot of molecules that are going to be moving super slow. In addition, there's not really going to be a whole lot of molecules over here that are moving super fast. Most of the molecules are going to be in the middle area, will peak at some location. Now, this graph, we're going to refer to these later on, but what they have here is the RMS speed is over here. So it's the higher of the three different speeds. Not as many particles are moving at it, but it is still a useful thing to talk about. We have an average speed, which is pretty much right in the middle of the curve, and then we have VP, which is standing for the most probable speed, which is where the peak is. One thing to note about this, the graph always starts at zero, but it never will end up reaching zero, reaching the x-axis on this side. So if you were ever asked to draw the distribution curve, just make sure that it never actually touches the axis. Because again, the idea is that there's going to be, you know, some molecule that's going at some speed that we don't know of. So that's why we're kind of leaving it there as an uncertainty. Now, there actually is an equation to figure out. We're going to use what's called a Maxwell distribution for these particles. And what we have is this. So this is saying how many particles are moving at some certain speed. Really quickly, you do not need to know this. I just want to show you kind of where it's coming from. And this is going to help us figure out the equation for the most probable and the average speeds. But the whole thing is this equation is actually relating to this graph and will tell you how many particles are moving at any speed based off of the temperature and the mass. Now, one thing to note is that when you take the average, or sorry, not the average, when you take the integration of this function, you end up getting the number of molecules n. Because again, if we're adding up all the molecules that are moving at all the speeds, well, it should equal up to the total number of molecules that we have. This basically means that every time we make a distribution curve, we need to make it so that the area underneath it is constant. More about that in a second. All right, so here, what it's saying, here's an example of how three different temperatures, what the graph would look like. So as we see here, the higher the temperature, the lower this peak is because this peak gets shifted over to a faster speed. So 100 Kelvin has a lower average speed than something like 700 Kelvin, where the molecules are going to be moving much faster. So that means this peak needs to be shifted over to the right. Now, as I said before, the area underneath the curve has to remain the same. So if we move the peak over to the right and it still has to start at zero, well, that means that the curve begins to flatten out. So as this moves to the right, the curve gets flatter and flatter. So the distribution ends up being much wider. So here we can already see that when it's colder, we end up getting this like a small section of particles, or a lot of particles moving in a very small distribution of speeds. But as it gets hotter and hotter, that distribution of speeds gets a lot wider. Likewise, if we do this for different masses, we get almost the reverse, that the heavier the object, then the higher the peak ends up being. This kind of makes sense because if they're all given the same amount of if they're given the same temperature, so they all have the same average kinetic energy, then the heavier the object, the slower their speed is going to be. So the heavier objects will have a higher peak, and then once again, as it gets lighter and lighter, that distribution will start to flatten out because of the fact that it's now able to go faster and faster. All right, so you do want to just recognize how the graphs kind of look with the whole increasing the temperature or increasing the mass. And again, another idea is the fact that when you make the curve, you want to make sure that your curve always starts at 0 and that you always make it so that as this peak shifts to the right, it goes lower and lower and lower and becomes more flattened. All right, so as I said before, the three different speeds, the RMS, the average, and the most probable, aren't exactly the same. It's going to be very rare that they will be the same. So what we want to do is figure out what these two are. So what we can do is we can figure out the average by doing something like this. Now, if you remember, average is pretty much adding up all the terms and dividing it by the number of terms. So what we can do is just take the um, adding up this is actually considered like a what's the exact phrase? A weighted average. So we take the speeds, times it by the number of molecules that are actually moving at that speed, add them all up from 0 to infinity, and then divide it by n, and that's an average. So if I take the Maxwell distribution that I have, I end up getting this. All these terms get pulled out. So if I take the integral of this, we end up getting this as my integration. Again, don't have to worry about it. It's fine. I'm just quickly showing how the numbers come up. And what this ends up simplifying to is radical 8 over pi kt over m, which is roughly about 1.6 radical kt over m. Now, the most probable is the very peak of it. So that's where the curve actually ends up having a zero slope, because that's what happens at the peak of something. So what I can do is I could take the slope of the Maxwell distribution and set the slope equal to 0. So I take the Maxwell distribution that's given to me, take the derivative of it with respect to v, set it equal to 0, and what I end up getting is this, radical 2kt over m, or 1.41 rad kt over m. So what this ends up giving me is this relationship that the most probable speed is always the lower speed. Then we have the average speed, and then we have the RMS speed, and that they're always going to be related using these coefficients. So it's always going to be one of these times rad kt over m. So what you could do is you can actually just record these down. You can actually record this, that VP is rad 2, V average is rad 8 over pi, VRMS is rad 3, and that each one is going to be times rad kt over m. All right, so here's another question. You could pause the video, work on this stuff, and we'll go over it in a second. All right, so what we want to see is what temperature will allow for the average speed to be equal to the escape velocity of Earth for oxygen helium atoms. So the oxygen, we actually kind of already got these masses from before, but we're taking the 32 molar mass and we're multiplying it by the 1.66 number to get this mass. Then we plug it into the average speed equation, the one with the 8 over pi, solving for temperature. We end up getting 1.9 times 10 to the 5th Kelvin. So a fairly high temperature in order for oxygen to escape the Earth's atmosphere, which is pretty much one of the reasons why we end up having oxygen on Earth and not all of it is actually escaping. We could do the same thing for helium. Helium has a molar mass of 4. So when we plug that in, we solve for the temperature. We end up getting 2.37 times 10 to the 4th Kelvin. So a little bit lower. 1.9 times 10 to the 5th versus 2.3 times 10 to the 4th. So it is one of the reasons why helium actually does escape from the Earth's atmosphere a little bit more often than oxygen, let's say. All right, so we're gonna end this lecture on that, and then we're gonna talk in the next part a little bit more about some other things that happen with gases and how that's relating to what's going on at the microscopic level. All right, if you have any questions, feel free to contact me and let me know. Otherwise, I'll see you later.